Welcome back to Basic Electronics. We will now start with a new topic, namely op-amp circuits based on positive feedback. First, we will take a qualitative look at positive and negative feedback and revisit our old friends, inverting and non-inverting amplifiers in this context. We will then look at the Schmitt trigger circuit, which is based on positive feedback. Okay, let us start. Let us now discuss feedback, and our discussion will be qualitative in nature. And let us start with this inverting amplifier circuit, which we have seen before. And if you recall, we had mentioned earlier that these connections are very important. So if we interchange the inverting and non-inverting terminals, the circuit would not work as an amplifier. And now let us see, at least qualitatively, why it would not work as an amplifier. Let us start with VO equal to AV times V plus minus V minus. And this equation holds if the op-amp is working in the linear region. Now, since the op-amp has a high input resistance, this current is 0, and therefore IR1 is equal to IR2. This current and this current are equal. And in this situation, we can obtain V minus using superposition, and this is what we get. And from this equation, we note that if Vi increases or Vo increases, then V minus will go up. All right. Now let us perform a thought experiment, so to say, in which Vi is increasing. So this voltage is increasing. As a result, what happens to V minus? Vi appears here, and that is increasing. So therefore, by equation 2, V minus will also increase. Now, as V minus increases, by equation 1, Vo will decrease because this V minus appears with a negative sign here, and therefore Vo decreases. If Vo decreases, this term decreases, and therefore V minus decreases. So that is what we have here. In other words, we have these opposing trends over here. An increase in V minus causes a decrease in V minus, and this is a negative feedback situation which makes the circuit stable, and therefore we can proceed with the analysis that we carried out earlier. Alright, let us now consider this same circuit with the plus and minus terminals interchanged and see what happens. In this case, V plus is given by this equation here, similar to this equation. And now let us imagine that Vi has increased. What would happen as a result? V plus would increase by equation 3. If V plus increases, Vo will increase by equation 1, and if Vo increases by equation 3, V plus will increase. And now we see that this trend is the same. V plus increasing causes V plus to increase further, and this situation is called a positive feedback situation. And what happens is, as a result, Vo rises or falls indefinitely, limited finally by saturation. So Vo will reach either plus Vsat or minus Vsat. And of course, the circuit cannot be used anymore as an amplifier. Let us now look at the feedback situation in a non-inverting amplifier. Here is the circuit. Once again, we have Vo equal to Av times V plus minus V minus, and this V plus is the same as Vi here. Since the op-amp has a high input resistance, this current is 0 and IR1 is equal to IR2, and in this case V minus can be obtained simply by voltage division. So that is Vo times R1 by R1 plus R2. That is our equation 2. Now let us imagine that Vi has increased Vi is the same as V plus. If V plus increases, Vo will increase by equation 1. If Vo increases, V minus increases by equation 2. If V minus increases, because of this negative sign, Vo will decrease. And we see that this is a negative feedback situation because these trends are opposite. So the circuit is stable and we can proceed with our analysis. Let us now see what happens if we interchange the non-inverting and inverting terminals, giving us this circuit here. In this case, V plus is given by voltage division. That gives us this equation 3. And let us now imagine that Vi has increased. What is Vi in this case? Vi is the same as V minus. And if V minus increases because of this negative sign, Vo will decrease like that. If Vo decreases, V plus will decrease by equation 3. And if V plus decreases, Vo will decrease by equation 1. So clearly we have a positive feedback situation because these trends are the same. A decrease in Vo will cause a further decrease in Vo, and as a result Vo will rise or fall indefinitely, limited finally by saturation. And this circuit of course cannot be used as an amplifier. Let us summarize. Here is the inverting amplifier with the plus and minus input terminals interchanged, and here is the non-inverting amplifier also with the plus and minus input terminals interchanged. And as we have seen, both of these circuits are unstable because of positive feedback. And the output at any time then is only limited by saturation of the op amp. So Vo here or Vo here will be plus minus Vsat. Now the question is, of what use is a circuit that is stuck at Vo equal to plus Vsat or Vo equal to minus Vsat? It turns out that these circuits are actually useful, and let us see how. Let us look at this circuit, which is our non-inverting amplifier with the plus minus inputs interchanged. R2 is 9K, R1 is 1K, and we will assume Vsat to be 10 volts. Now as we have seen, because of positive feedback, Vo can only be either plus Vsat or minus Vsat. It will be plus Vsat if V plus is greater than V minus, otherwise it will be minus Vsat. Now let us take an example. Say Vi equal to 5 volts. So we have 5 volts here, and figure out whether the output would be plus Vsat or minus Vsat. Let's take case 1 first, in which Vo is plus Vsat. So we have 5 volts here, we have 10 volts here. If this is 10 volts, then by voltage division, this V plus would be 1K divided by 10K times 10 volts or 1 volt. And the situation now is V plus is 1 volt, V minus is 5 volts. So V plus is smaller than Vi or V minus, and therefore Vo should actually be minus Vsat. So clearly there is an inconsistent situation here, and therefore this cannot happen. So what happens in this case is Vo is equal to minus Vsat, and let us check quickly whether that is consistent or not. So we have 5 volts here, minus 10 volts here, and by voltage division V plus would be minus 10 times 1 by 10 or minus 1 volt. So V plus is minus 1, V minus is 5, and therefore Vo would be minus Vsat, and everything is consistent. Let us show that data point on this plot here. What are we plotting? We are plotting V plus as well as Vo as a function of Vi, and right now we have only one data point, that is Vi equal to 5. For Vi equal to 5, we have V plus equal to minus 1 volt and Vo equal to minus 10 volts. That is the same as minus Vsat. And if we move to the right, that is increasing Vi, the same situation applies and Vo remains equal to minus Vsat as shown here. So in this entire range, Vo remains equal to minus Vsat and V plus remains equal to minus 1 volt. Okay, so we have got this part of the Vo versus Vi relationship, and now let us consider decreasing Vi. So that means we are going in that direction, and V plus, as we have seen, is Vo times R1 by R1 plus R2, and since Vo is minus Vsat, V plus is minus 1 volt, and that is what we have shown here as well. Now as long as Vi, which is the same as V minus, remains greater than V plus, Vo will remain at minus Vsat. And what is V plus? V plus is minus 1 volt. So up to this point, things will not change. If Vi is decreased further, that means it goes below V plus, which is minus 1, then Vo will change sign. Vo will become plus Vsat, and that is shown over here. And if Vo changes, V plus also changes. It will now become R1 by R1 plus R2 times plus Vsat, or plus 1 volt. So V plus has also changed from minus 1 volt to plus 1 volt here. And if we go on decreasing Vi further, what happens? This V plus is equal to 1 volt and we are decreasing this Vi further. So nothing is going to really change because V plus will remain larger than Vi, and that is what we get if we go on decreasing Vi. Now the threshold at which Vo flips is plus 1 volt. So now imagine that we are increasing Vi in that direction and V plus is sitting at 1 volt. When Vi crosses that 1 volt, the output is going to change again, like that. So that is our Vo versus Vi relationship, and we see this strange part here which is called hysteresis. Here is the Vo versus Vi relationship again, and this circuit is called the inverting Schmitt trigger. And let us summarize the salient features now. First, there are these threshold values, lower threshold and higher threshold. The lower threshold is called VTL and the higher threshold is called VTH. And these threshold values are also called tripping points, denoted by VTH and VTL. And as we have seen in the last slide, they are given by plus minus R1 by R1 plus R2 times Vsat. Now which tripping point applies really depends on where we are on the Vo axis, and that is a big difference between this circuit and other circuits we have seen earlier. For example, if we are here, then the tripping point that is relevant is this one, VTH, and that is also the reason we have used these arrows here. If we are here and we keep reducing Vi now, then the tripping point that is relevant is this one, VTL. So in that sense, the circuit has a memory because its behavior depends on the past. What is the past? That is whether Vo was high earlier or whether Vo was low. And this quantity delta Vt, which is the difference between VTH and VTL, is called the hysteresis width. this width here. Let us now look at the non-inverting Schmitt trigger, which is obtained from an inverting amplifier by interchanging the inverting and non-inverting op-amp inputs like that. And as we said earlier, because of positive feedback, VO can only be either plus Vsat or minus Vsat. Plus Vsat if V plus is larger than V minus, and minus Vsat otherwise. So let us take an example, say Vi equal to 5 volts, and see whether VO is expected to be plus Vsat or minus Vsat in this case. Suppose VO is minus Vsat, so this VO is minus 10 volts. What is V plus then? This current is 0 and V plus can be obtained by superposition. So we have Vi here and VO here. Consider these two as independent voltage sources, and then we get this expression here. So R2 by R1 plus R2 times Vi plus R1 by R1 plus R2 times VO. R2 is 9K, R1 plus R2 is 10K. So 9K by 10K times Vi, which is 5 volts, plus R1 1K, R1 plus R2 10K times VO. VO we have assumed to be minus 10 volts, minus 10. So that turns out to be 3.5 volts. So V plus minus V minus is 3.5 minus 0. So obviously V plus is greater than V minus, and therefore VO must be plus Vsat. And clearly there is some inconsistency here, because we started assuming VO equal to minus Vsat and we ended up with VO equal to plus Vsat. So clearly this is not going to happen. So what does happen is VO becomes equal to plus Vsat, that is plus 10 volts, and let us now check whether that is consistent. So let us first find V plus from this same expression here. 9K by 10K again times Vi, which is 5 volts, plus 1K by 10K times VO, which is 10 volts. So that turns out to be 5.5 volts. So V plus is 5.5, V minus is 0. So therefore VO is plus Vsat, and that is consistent with our original assumption. So that is the data point marked over here. VO is 10 for Vi equal to 5 volts, and at that input voltage V plus is 5.5. Now if we move to the right, that is in the direction of increasing Vi, what do we expect to happen? It turns out that VO remains equal to plus Vsat. Of course V plus is not constant anymore, because V plus varies as Vi varies. So the relationship between V plus and Vi is a straight line, and the slope is positive, and that is what we get. And now what we want to do is, as we decrease Vi, we want to see what happens. Alright, now let us see what we expect as Vi is decreased. V plus is going to decrease, because as we saw in the last slide, V plus is proportional to Vi, and at some point V plus would become negative, and at that point VO will flip from plus Vsat to minus Vsat, and let us see when that happens. So consider decreasing values of Vi. V plus, the same expression as we saw earlier, R2 by R1 plus R2 times Vi plus R1 by R1 plus R2 times VO. So that is 9 by 10 times Vi plus 1 by 10 times VO. Now as long as V plus is positive, VO will remain equal to plus Vsat, like that, and that happens up to this point. So V plus is positive, just positive at this point, and if we decrease Vi further in that direction, then V plus is going to cross 0, and then VO is going to flip from plus Vsat to minus Vsat. And when does that happen? When does V plus become 0? For V plus to become 0, this expression has to become 0, and that gives us Vi equal to minus R1 by R2 times Vsat, which is minus 1 by 9 times 10, or minus 1.11 volts. So when Vi is minus 1.11 volt, then VO changes sign, that is, it goes from plus Vsat to minus Vsat. So this is how VO has changed from plus Vsat to minus Vsat. What about V plus? V plus is given by this equation, the same equation as this one, except now VO has become minus Vsat. At this point, Vi is minus 1.11 volt, as we saw earlier. So this term is already negative, and this term is also negative now because VO is minus Vsat. So the net result is, at this point, V plus is a negative number. We can calculate that. Alright, so now what happens as we continue to decrease Vi further in that direction? V plus is proportional to Vi. So as Vi is decreased, V plus will also decrease, and at this point V plus is already negative. So what will happen? V plus will keep going down, it will become more and more negative as Vi is decreased. If V plus continues to be negative, that is less than V minus, VO will then continue to be minus Vsat, and we would expect VO to stay at minus Vsat. And let us now look at the equation that V plus will follow in this region. V plus is given by this expression, same as this one, except now VO has become minus Vsat. So we have V plus equal to 9 by 10 times Vi minus 1 by 10 times Vsat. So V plus versus Vi is still a straight line with a positive slope, but now the x-intercept has changed. So we will now have this line here, and its x-intercept would be somewhere there, like that. Okay, now let us consider Vi increasing. So we go in that direction now, and V plus will also increase, and at some point V plus will cross 0, and that is where VO will flip from minus Vsat to plus Vsat. And what is Vi at that time? So what is the threshold? That is given by V plus equal to 0. So we have 0 equal to 9 by 10 times Vi minus 1 by 10 times 10. So Vi turns out to be R1 by R2 times Vsat, or plus 1.11 volts, like that. And now if we keep increasing Vi, VO will not change, and we have completed the VO versus Vi picture. Let us summarize the situation for the non-inverting Schmitt trigger. Here are the threshold values VTH and VTL. VTH is given by plus R1 by R2 times Vsat, and VTL is given by minus R1 by R2 times Vsat. And as in the inverting Schmitt trigger, this circuit also has a memory. Why do we say that? Because the tripping point or the threshold point depends on where we are in this VO versus Vi plane. If we are here, and if we are increasing Vi, then the tripping point is Vth. If we are here and if we are decreasing Vi, then the tripping point is Vtl, and that is indicated by these arrows here. Once again, delta Vt equal to Vth minus Vtl is called the hysteresis width. Here is a summary of both types of Schmitt triggers which we have seen, inverting and non-inverting. The inverting Schmitt trigger is denoted by this symbol here, and the non-inverting Schmitt trigger by this symbol. Essentially, this symbol comes from the VO versus VI relationship. Alright, the VTH, VTL expressions are also included here, and it's a good idea to turn off your monitor at this point, draw the circuits, go through the derivation in your mind, and come up with the VO versus VI relationship for each of these Schmitt triggers. And also remember to derive the expressions for VTH and VTL rather than remembering these. To summarize, we have started looking at a different class of circuits in this lecture. In contrast to the circuits we have seen earlier, the circuits we have seen today, the Schmitt trigger circuits, are based on positive feedback. In the next class, we will look at some applications of the Schmitt trigger. Until then, goodbye.